Okay, once we have our electrolytic cell or voltaic cell set up, we also want to be able to look at how much potential is going through it. Potential is just the voltage that the cell carries. So if we're making a voltaic cell to act as a battery, we need to know how many volts it creates. So cell potential just describes this driving force or this voltage. A positive cell potential means that we have a spontaneous reaction that can do work, but a negative cell potential means that we have a non-spontaneous reaction that cannot do work but needs work done to it. So our spontaneous reactions have a positive E cell value. E cell is our cell potential. Now when we describe our two half cells, our oxidation and reduction, that create a whole reaction, we can look up the cell potential of every half reaction. So for every silver that loses an electron to become silver 2+. Okay, so in order to look at our electrochemical cell, and in this case we're going to talk about a voltaic cell, we need to be able to describe the cell potential. How much voltage is going through the cell? So if we're creating a battery, we need to know the volts. So cell potential is a measure of that voltage, the driving force. And it is symbolized by capital E, cell, and the little 0 of course means standard state, and we'll talk more about that. If we have a positive E cell value, it means that we have a spontaneous reaction that can do work, so it would act as a battery. If we have a negative E cell value, it cannot do work. It's a non-spontaneous reaction, and it would require work done to it. We can calculate this cell potential by using half reaction cell potential, and we'll look at that, for the two half reactions in our reaction. So our oxidation and our reduction would be half reactions each, and we put them together to make a whole reaction. All of our cell potentials that we're going to look at on the table are written as reductions. So we're going to look at how to use that. So our cell potential is a newer term for electromotive force. In physics, they still call it electromotive force. It's EMF. But we call it cell potential, and it's really just measuring the voltage. So we need a positive E cell value for a spontaneous reaction in order for it to do work. And just like our delta G described spontaneity, and the more negative delta G is, the more spontaneous, the more positive the E cell value is, the more spontaneous, and the more work it can do. So we need to talk about units for a minute, because we're going to be looking at some different unit values. So cell potential, or electrical potential, is measured in volts, which will be capital V. Electrical charge, which has to do with the electrons, charge of electrons, is measured in coulombs, which is capital C, and we'll talk more about coulombs later. Work that is done by the cell is measured in joules, because work has energy units. So we'll look at that. And when we look at how these combine, 1 volt going through a cell is equal to 1 joule of work per coulomb of charge. So voltage is actually a ratio of joules to coulombs. And that's going to be an important idea in a minute. Here's some examples of voltage going through different voltaic cells or batteries. You're probably familiar with the alkaline batteries like AA, AAA, C, D batteries that you might put into a flashlight or a radio or a remote control. We also have 12-volt batteries that are lead-acid batteries to run cars. Your 12-volt battery is not really one cell, it's actually 6 cells that run 2 volts each. They're just run together. The little round silver batteries you put in calculators or hearing aids are mercury normally, and they're 1.3 volts. Your laptop, your cell phone potentially, although they moved away from this, and a lot of the newer power tools are lithium-ion batteries that produce 3.7 volts. So they produce a lot more voltage, which can use them to power more things. They're also much smaller considering the amount of voltage they make. But they're more reactive, which is why you had the problem with people's cell phones exploding. But they're not bad batteries. And then, of course, for biologists out there, electric eels that can produce electrical charge have 5,000 of these cells that are 0.15 volts each, which adds up pretty quickly. Alright, so when we think about how much voltage is going through our cell, we need to compare it to something because voltage is a ratio. And we use standard cell potential, just like we've had standard state for our delta G and for our entropy, to describe the conditions of the voltage. So just like the others, we have pure solids, pure liquids, 1 atmosphere for gases, 1 molar for solution. And in this time, we actually have 298 Kelvin as a temperature for standard state. Standard state is what we use to create the tables. If you look up standard reduction potentials in your book or online, you will see long tables of half reactions with a voltage value associated with them. So if we look at this table, we have F2 plus 2 electrons, so gaining electrons to create 2F minus. So this is a reduction, and it has a numerical value associated with it in terms of volts. This table is organized with the largest voltage on top and decreasing as it moves down the table. So you'll notice that we have positive voltage values, and then it switches to negative. So remember, positive voltage means it's spontaneous. Negative voltage means it's non-spontaneous. So for this table, it means that as a reduction, because all of these are written as reductions with our electrons on the left side, as a reduction, the first part of this table is spontaneous. But the bottom part of the table is non-spontaneous as a reduction, meaning it would rather be oxidized than reduced. And if we look at what's on the table, we can see how this makes sense. The most positive as a reduction is our fluorine. Fluorine wants to pick up electrons. It's very electronegative. So picking up electrons and being reduced is going to be spontaneous for fluorine. And if you look at the other ones on this list, you can see that makes sense. Gold picking up electrons, chlorine and oxygen, again, very electronegative. They're going to pick up electrons, bromine, also in the halogens. Alright, so several of these we can tell more electronegative, wanting to pick up electrons. They're going to be spontaneous as reductions. The bottom part of this table, we have mostly family 1 and 2 ions. Remember, they are not very electronegative at all. They don't want to pick up electrons. They'd rather give electrons away. So as a reduction, they are non-spontaneous. So if we look at 2 half reactions we want to put together for a voltaic cell, we pick out the 2 that we're interested in. So in this case, I have nickel 2 plus, adding 2 electrons to create solid nickel, and silver plus, picking up an electron to form silver solid. And these are the 2 values from the table. So nickel is negative, meaning it doesn't want to be reduced, it would rather be oxidized. And silver is positive, meaning it likes to be reduced. So if I want to put these 2 half cells together to create a voltaic cell, I need to write them in the direction that is most favorable or spontaneous. So silver would rather be reduced, Nickel would rather be oxidized. So that's the way I'm going to write it. Okay, we're going to reduce the silver from Ag plus to Ag, and we're going to oxidize the nickel from nickel solid to nickel 2 plus. So what is our cell potential when we do that? There are two ways to solve for cell potential. I'm going to describe both ways. You need to figure out which way makes the most sense to you and stick with it. Okay, don't try to do them both. Don't try to put them together because it gets very confusing. Just pick one method and go with that. Alright, the first method, we're going to take the reduction potential from whichever one is being reduced, and we're going to keep it like it is. We're going to flip the sign on the oxidation half reaction. So if it's positive, it becomes negative. If it's negative, it becomes positive. And then we're going to add the two values together, the reduction plus the flipped oxidation. And that will give us the overall potential. So that's method 1, and we'll look at an example of that in a minute. Method 2, we have an equation. Our cell potential is equal to potential of the cathode minus potential of the anode. So our cathode has our reduction reaction, our anode has our oxidation. So in this case, we would take our silver minus our nickel, the values directly from the table without changing anything, to get our E cell. Alright, so here's our method 1. This is taking the reduction potential as is, flipping the oxidation, and adding. So this is our flip and add method. So here's our two half reactions we got from the table. We know that we're keeping silver as it is. This is our reduction. We're going to flip the nickel reaction around. So here I flipped it, so I have nickel solid going to nickel 2 plus. And I flip the sign on the potential. Then we add the two values together. We can add the two reactions together to get our total cell voltage, or cell potential. Now notice when I added these two together, I had to double the silver equation, so it would have 2 electrons each, just like we did when we were balancing half reactions. Our electrons have to match. So I'm going to multiply my silver times 2 before I add it. But I did not change the E potential. I did not multiply it by 2 or anything else. Remember, potential or voltage is a ratio, so we don't need to multiply it by a cofactor. Alright, that was our first method. Here's method 2. Method 2, we use the equation. We're just going to fill in the values from the table, and we have our cathode reaction, 0.8, minus our anode reaction with the negative, so I'm not changing this. It goes directly into the equation like it is from the table, but subtracting a negative makes it positive, and we get the same voltage as before. Alright, so pick whichever method makes most sense to you and stay with that. Now a couple of things with our cell potential. Flipping the half reactions flips the sign. So if you're doing the flip and add method, when you flip it around, it flips the sign around. Even if you have to multiply by a cofactor to match up electrons, do not change the E cell potential. It does not get affected by coefficients. Alright, so let's look at this example. And in the next video, I'll work out all of the math and write everything out. But we just want to look at, in this video, what's going to be our anode, what's going to be our cathode, which direction is this going to run. So we have gold 3 plus going to solid gold, value 1.5 volts. Copper 2 plus going to copper solid, value 0.34 volts. So we need to assign one of the half reactions as the reduction and one as the oxidation. They're both written as reductions. From the table, they're all reductions. So we need to pick the one that is most likely to be reduced to act as our cathode. So we're going to pick the larger value. In this case, it's the gold. The gold is more likely to be reduced. It's more spontaneous as a reduction. So we're going to keep that one. And we're going to flip the copper as the oxidation. All right, so that means we would have 1.5 minus 0.34 if we're doing the equation, or we would have 1.5 plus a negative 0.34 if we're doing the flipping and adding. So in this case, our gold would be our cathode as part of the reduction. Our copper would be our anode as part of the oxidation. Alright, because we have oxidation and reduction half reactions, we also have oxidizing and reducing agents, just like we talked about with our equations. Set up in the cell potential table, because they're ordered based on cell potential, they're also ordered based on oxidizing and reducing power. Alright, so something that is more easily reduced is a stronger oxidizing agent. Remember, oxidizing agents get reduced. So the stronger the oxidizing agent, the more likely it is to be reduced. So the more positive the E cell value, the stronger the oxidizing agent. The more negative the E cell value, the stronger the reducing agent. All right, so it can go in order. So in this case, we have copper. Hydrogen is our standard reference cell because it has a value of 0. Everything is based on the hydrogen. And then we also have zinc. So copper is positive, our hydrogen is 0, our zinc is negative. So copper is going to be a stronger oxidizing agent. Zinc is going to be a stronger reducing agent. Alright, with this cell potential, we need to talk about how this relates to free energy, or our Gibbs free energy. Because cell potential is telling us which way is spontaneous, just like delta G is, just like our equilibrium K value, we know that they have to be connected. And we've already talked about one connection between delta G and K. We've talked about this equation. Now we're going to talk about the relationship between delta G and E, and then our relationship between E and K. And so in this video, we're just going to look at the concept, and the next video we'll look at doing the calculations. So our cell potential, if it's positive, it's a spontaneous reaction, electrons flowing from the anode to the cathode. Negative cell potential, it's a non-spontaneous reaction, we need a power source. If cell potential is 0, we don't have a favored direction, just like we've talked about with delta G. That means we're at equilibrium, and our cell no longer will do work. So we have a very strong connection between E cell potential, our delta G free energy, and our equilibrium K value. This is the equation between delta G and E cell potential. So our delta G value is equal to negative N, which is our number of electrons that we transfer, we'll talk about that in a second, times Faraday's constant. For right now, that's just 96,500. We'll get to what Faraday is in a couple of videos. And our E cell potential, which is how many volts are running through our cell. Alright, so when we're looking at relating our delta G to our E cell, we have to know how many electrons are running through our cell potential. So that means we need to take the number of electrons that we had to get between both half reactions. So remember when we were balancing the half reactions, and we would have 3 electrons in one half reaction and maybe 2 in the other, and we would multiply by cofactors, and that would give us 6 electrons in each. That N value would be the 6 electrons. Alright, so the N value is how many electrons were being transferred. F is our constant, our Faraday. Notice this is in joules. Alright, and then our E cell potential that we get from calculating from the table values. When we multiply all those together and then have a negative sign because delta G is inverse, we get our relationship between delta G and E cell. Then our other equation we've already looked at relating delta G and K is the second one. And now we're going to put those two together. Since they both equal delta G, we're going to set them equal to one another. And we're going to rearrange for E cell. So dividing by our minus n times F over here, we get positive RT, where R is our gas constant in energy units, T is our temperature in Kelvin, over our N, number of electrons transferred, times F, our Faraday, times the ln of our K equilibrium. This is only going to work at standard conditions, so we have the standard 0. Okay, only at standard conditions. We'll talk about non-standard too. Alright, so for our summary of our concept, we have 3 different values that can tell us spontaneity and reaction direction. Our E cell is measuring it in terms of potential or voltage going through our cell. Our delta G tells us how much work we can do, and our K value tells us where the equilibrium lies. Alright, so we have 3 different equations in order to move between the different values, between E cell and delta G and K, and E cell and K. This table gives you some idea about what we can look for to determine reaction direction. We already know negative delta G is spontaneous, positive E cell is spontaneous, a K larger than 1 is spontaneous. Delta G positive is non-spontaneous, E cell negative is non-spontaneous, K less than 1 is non-spontaneous. And at equilibrium, delta G and E cell are 0, and we no longer have a